We're going to start today by talking about something called the regression model. And for the sake of understanding the regression model, we'll do some simulation to help us understand what the model is about, and then what we do with statistical inference in this context. We've got a random sample in the case of simple linear regression with one explanatory variable, x, and one response variable, y. Y responds to x is the idea. And in the random sample, you, for the sake of clarity in your theory, you really make the first coordinates lowercase, indicating that those are going to be fixed numbers, not random variables. And it's the corresponding y values that are the random variables. So you use uppercase letters. So lowercase for the x values, uppercase for the y values. This is the form of the random sample. This is a random sample. The y's, though, depend not just in a random way based on some probability model, but also they depend on x. We assume, this is a big assumption, we assume the curve of regression of y on x is a linear function. Remember mu sub y given x from chapter 5? That's the curve of regression. Back in chapter 5, we had to compute the curve of regression when we had a joint distribution for x and y. We had to compute marginal densities, conditional densities by doing integrals, and ultimately do an integral to compute this mean. But here we're doing something different with this. We're assuming something about it. We're assuming it's a linear function of x. And the standard notation for the slope and intercept, instead of b1 and b0, it's the Greek versions, beta 1 and beta 0. In fact, I'll put the intercept first, that's standard. Beta 0 plus beta 1x. That's a linear function of x. That's why this is called linear regression, or at least the linear part. The word regression has another meaning, which we'll have to come back to later. We also assume each of the capital Y's can be found with what you might call a signal formula and a noise formula. I'll just write signal plus noise. The signal refers to the linear pattern. The noise refers to random error, you might say. The signal is the mean, effectively. The noise is a random error. And by the assumption that we're making about mu, this can then be written as beta 0 plus beta 1 x plus EI. And I really should plug in the actual value x sub I here. So I'll use subscripts on the x as well. So part of the model is the assumption that mu is a linear function of x. Another part of the model is assumptions about these e's, these errors, this noise, or you may maybe call it static, okay? There are random errors, you might say, that come in because of randomness in real life. That happens. we're going to assume also that each of these EIs is normally distributed with a certain mean and a certain variance. These are errors. Intuitively, you imagine errors could be positive or negative. The Y values could be sometimes above their mean, sometimes below their mean. And that would imply these errors are sometimes positive and sometimes negative. Seems reasonable to assume their mean is 0. But they're going to have some variability. How do you measure the variability? Well, I guess with some sort of variance. Call it sigma squared. Part of using the regression model is to try to estimate sigma squared. That's part of what you do. There's an estimator that you're going to use for sigma squared called the regression standard error. That's part of the point. As well as using the sample regression line to estimate the population regression line to estimate beta 0 and beta 1. So what I'd like to do now is just go to a spreadsheet and do some simulation of this to give us some intuitive feel for what's going on here. So I'm going to have a column for X values, observed X values, which you don't think of as random variables. You think of these as fixed. And then a column of observed values of capital Y. Now, again, capital Y is going to be a random variable. But here, these are going to be observed values, so I'll call them little y's. And let's pretend the true population regression line, which is what we are talking about here in the model, is the population. Right? We always use Greek letters for populations. Let's pretend, just for the sake of simulation, that we know what it is. Right? In real life, hardly ever would you know what beta 0 and beta 1 are. Exactly. You're trying to estimate it. You wouldn't know what sigma squared is either. You're trying to estimate it. But just for the sake of example, suppose beta 0 is 1 and beta 1 is, say, 0.5. So mu of y given x is 1 plus 0.5x. That's the signal. That's the deterministic part of the model. The noise is the random part. Stochastic part is another word people use. So I'm going to use this equation, and I'm also going to use some randomness to simulate the e's. On purpose, I'm going to pick values of x that repeat sometimes. Well, let's start with 1. Let's make there be 5 1s. There's 5 1s. Now let's add 1 to those numbers, like that, to get a bunch of 2s. How many 2s? Well, let's just do 5 2s as well. Oops, wasn't supposed to do that. That's because I need to paste special, not the formula. Actually, let's do $$6 there to keep that cell reference fixed. Now I got a bunch of 2s. Maybe I want a bunch of 3s as well. $A, $11 plus 1. Say 5 3s. Keep going. How far should I go? I don't feel like going too much further. How about we get 5 4s and also 5 5s? In the ideal world, when you are using linear regression, you do have a lot of data, and some of the data, the X values repeats. That's kind of the ideal theoretical world for linear regression. Doesn't always happen in practice. So what am I going to do here? First, I want the deterministic part, the linear model, 1 plus 0.5x. So I'll type equals 1 plus 0.5 times A2 there. If that's all I do, and if I copy and paste that, there's no randomness, right? That would just be a bunch of deterministic stuff, pre-calculus stuff. I want to bring in some randomness now from the distribution of EI. What should I assume about the distribution of EI? Let's also suppose EI is normal with mean 0 and variance 4, just to pick something. So the standard deviation would be 2. That's 2 squared. The standard deviation is 2. Norm inv in a spreadsheet. We'll do some simulation if you combine it with rand like this. What norm inv does is it really gives you X or Z values, depending on whether you're using the original distribution or standard normal distribution. The first input there, the X that you plug in, which is for me going to be rand, is a number between 0 and 1 representing a CDF value, a percentile value, you could call it. Like 0.9 would represent the 90th percentile. 0.8 would represent the 80th percentile. If I put comma 0, comma 1, it's going to give me Z values, critical Z values, when the CDF output is 0.9 or 0.8 or whatever. But I want to use the mean that comes from, well, the mean of 0, excuse me, and a standard deviation of 2. Because I'm assuming the EIs are normal with a mean of 0 and a standard deviation of 2, variance of 4. So this is giving me a random value of y. That's got, again, a deterministic part, 1 plus 0.5 times x, 1 plus 0.5 times 1, 1.5, plus an EI value, a random error, which if this part is 1.5 and I get an output here of 1.4685, the value of E must be negative. Negative 0.0315, I think. But again, as I copy and paste, everything changes. So what do we have here? We have a bunch of X values that repeat, 1s, 2s, 3s, 4s, and 5s, and the corresponding Y values that come from the regression model, a simulation of the regression model. It should be the case as I go down this list toward when X is 3, 4, or 5, that generally speaking, the Y values are bigger than they are over here. Yeah, that's true. That's because of the deterministic part, because of the 1 plus 0.5x having a positive slope, right? As X gets bigger, 1 plus 0.5x is going to get bigger. But these numbers don't get bigger monotonically. They jump up and down. That's because of the randomness. Let's make a graph, scatter plot of these things and see what we see. There's what we see. Let's try to get the regression line in there. The trend line is the regression line. Label, use equation. Show R squared, the squared correlation. And what do we see? I don't know if that's big enough for you to see that there. Looks like the line is y equals 0.3x plus 1.13, a slope of 0.38, and a y-intercept of 1.13. Squared correlation pretty close to 0. It's not a very strong linear trend. It is a slight positive linear trend. 0.38 is B1 and 1.13 is B0. Not beta 1 and beta 0, B1 and B0. Beta 1 or beta 0 is 1. 1.13 is our observed estimate of beta 0, our observed estimate of 1. We're pretending we know what the population regression line is here. The 0.38, B0, B1, excuse me, sample slope is an estimate for the population slope, 0.5. If I redo it all, right, it redoes the simulation. Just do a copy and paste here. I think it should be fine. It should be redone. It's redone. It's a new sample with a new slope and new intercept. R squared's a little further away from 0 this time. Do a copy and paste again. Get another one. So this is kind of a clunky way to do simulation to illustrate what's going on in the regression model. The trend line, the linear regression line, is the signal, the deterministic part. But for each one of those values of x, there's scatter about it. We have observed values of those random errors, the EIs, that are sometimes positive, sometimes negative. When the point is above the line, then the observed value, the EI, is positive. When it's below the line, it's negative. We're assuming that the EI's spread, the sigma squared, doesn't depend on x. Now, of course, in any run of a simulation, it will depend on x, and in particular, in this case, when x is 3, because of this outlier up here, there's a fairly large spread. And when x is 2, you can see there's a fairly small spread. That's going to happen with any simulation. It's going to happen with any real data. The model is idealized. And data is messy. We're trying to use the messy data to approximate the more idealized model. I do want to come back to doing more with regression on a spreadsheet, including showing you how to get some important kinds of output. But for the moment, I think it would be good to talk more about inference. To talk about estimators for beta 0 and beta 1 to be random variables. Oh, and what should we call them? How about capital B0 and capital B1? Capital B0 is going to be a statistical estimator, for beta 0, and capital B1 is going to be a statistical estimator for beta 1. What's going on here? It's so important for you to not just read and keep going, but to read and think as you read. These are statistical estimators. That means they're random variables. That means they've got distributions. If they're continuous, they've got a probability density function, PDF, cumulative distribution function. You can find their means, you can find their variances, possibly. I'm using capital letters here because these are estimators, random variables. Well, how are they defined other than with words? They are still defined with formulas. And for B1, let me remind you of how I remember these things. I remember B1, whether it's a capital B1 or a lowercase b1, as being a ratio of two sums of squares. SSXY divided by SSXX. I'm going to purposely put a capital Y this time instead of a lowercase y, but the x's are lowercase. Okay, I'm telling you how I remember these things. If I have a need to remember them without looking them up, this is how I remember it. So I start by remembering that the slope is a ratio of SS's. sums of squares. XX on the bottom, XY on the top. Whether I use a lowercase or capital Y depends on whether this is lowercase or capital. Remember, the X's are thought of as being fixed numbers chosen by the experimenter. The Y's are the response variables that are random. These kinds of perspectives are really important if you're going to fully get this and fully get how to apply it in real life. But what are the sums of squares? SSXX truly is a sum of squares. It's that. It goes from 1 to n. SSXY is actually not a sum of squares, but we use the SS notation anyway. It's a sum where the products that are being added are factors like this, but one of the factors involves X and one involves Y. And again, make the Y's capitalized and the X's lowercase. Turns out these things can be expanded. This is more important back in the days before calculators and computers to learn how to expand this for the sake of easier hand calculations. The one on the bottom ends up being the sum I goes from 1 to n of xi squared minus, it turns out, the sum of the xi's quantity squared over n. I didn't prove that just now. You're just trusting me. The reason I remember that is I taught it many, many times. And the one on the top is something similar where, except that one of the x's gets replaced with a y. In other words, you get sum I goes from 1 to n of little xi times capital yi minus a fraction, sum I goes from 1 to n of xi times sum I goes from 1 to n of capital yi, all divided by n. And then to get the formula in the book, take this crazy looking fraction with fractions within fractions and multiply the top and the bottom by n, which doesn't change its value, you might say, or what it is, because you're multiplying by 1, a disguised form of 1. So you get n times the sum I goes from 1 to n of xi times capital yi minus the n here cancels. So you get the sum of the x's times the sum of the y's, also multiplied by n on the bottom. So you get n times the first summation, the xi squareds, minus the n there cancels. So you get this. Again, all the x's are lowercase, all the y's are capitalized. All the x's are fixed numbers, all the y's are random variables. This is not a number. This crazy thing is a random variable because the y's are random variables. Check that I didn't make a mistake. Let's look at the formulas in the book. The book has some typos, though, that I need to alert you to. Page 387. That's what I just wrote down. Oops, I forgot to square it. I forgot to square this thing here. This thing right here. Same as this thing right here. Notice the book also labels that beta 1 hat. That's because it's an estimator for beta 1. Typos, in my book at least, right above this box, it says evident. It is evident that they are actually observed values of random variables, B0 and B1, lowercase r, which we denote by, no, not beta 1 and beta 2, but capital B0 and capital B1. That's one typo on this page. There's more. Can you see that? Is that dark enough? capital B0 and capital B1. Yeah, this is the formula I just wrote down. And then B0, capital B0 is capital Y bar minus capital B1 times lowercase x bar. The x's are fixed numbers, the y's are random variables. From these formulas, and from these model assumptions, which are related to what I was talking about 15 minutes ago, you can do a whole bunch of theory, a whole bunch of theoretical calculations that come up on the next couple pages, including crazy looking calculations like this. Actually, this is not much different than what I just did. I went in reverse, essentially. Calculations with expected values using linearity of the expected value operator. More crazy looking calculations. I'm not going through these details, by the way, in case that wasn't clear. Do you have to? Only if you really want to. To ultimately get to this box right here. Distribution of capital B1. Capital B1 is normal with mean beta 1 and variance sigma squared divided by that summation. And that summation, by the way, is none other than SSXX. I'll write it that way on the paper here. After a bunch of other work, Dr. Wetzel would always say size of the dots is proportional to the amount of work. So those are big dots. Right? If he ends up teaching applied stats in a year and a half, he'll probably say that in class a fair amount. Size of the dots is proportional to the amount of work. I made some big dots there, so there's a fair amount of work. B1 is normally distributed with a mean of beta 1 and a variance of sigma squared divided by, I'll just write it as SSXX. By the way, I don't remember if Dr. Wetzel uses the SS notation or not. I don't remember that. But I use it because I taught out of a business stats book that used it. So I got used to using it. SSXX at least is indeed a sum of squares. SSXY is not technically a sum of squares, but I go ahead and use the notation anyway. Hey, the mean is beta 1. What does that mean about B1? Pun intended. The mean of capital B1 is beta 1. What does that mean about capital B1? It's a blank estimator for what? Fill in the blank. Starts with a U. Unbiased. The expected value of B1 is beta 1. B1 is an unbiased estimator for beta 1. That's good. We like unbiased, especially with means. This fraction is the variance of B1. Take its square root, you get the standard deviation of B1. Wait a minute. I thought sigma squared was the variance. Why am I dividing by SSXX? Isn't sigma squared the variance? Didn't I just say that 15 or 20 minutes ago? You got to keep track of things. Sigma squared is not the variance of B1. It's the variance of each EI. By the way, I forgot to say, assume the EIs are also independent. We assume the EIs, E1, E2 through EN, are all independent random variables too, because it allows us to do the theory more easily. And we hope it's a somewhat valid assumption in practice. By the way, and that is the nature of applied math, especially this kind of math where you're using probability to do modeling in statistics. It is its very nature that you're making assumptions that are probably not exactly right. right? It's probably not true that the curve of regression is a linear function of x ever, in most important situations at least. Exactly a linear function of x? Seriously? Probably not. Except in places where you're forcing it, like the relationship between degrees Celsius and degrees Fahrenheit or something. That's a fixed deterministic relationship by definition. But in most real life situations where you're gathering data, probably never has the curve of regression been exactly linear. But we're going ahead and assuming it anyway. How can we get away with an assumption that's never been true? Well, we hope it's just approximately true. Good enough to get good answers. That's what you got to do in mathematical modeling, is hope your assumptions are good enough to get good answers. Most advanced mathematical modeling, at least. I'm not talking about mathematical modeling where you're just doing basic arithmetic or something. I'm talking about this kind of modeling. Yeah, and it's normal. That's got to be part of your assumptions too. That's got to be based on the fact, I suppose, that the EIs are normal. If we didn't assume the EIs are normal, then probably beta 1 would not be normal either. It's got a distribution. It's got a sampling distribution. Sampling distribution. Of capital B1. Don't say sampling distribution of beta 1. That doesn't make any sense. Beta 1's a fixed number. Capital B1's a statistic, which is a random variable. It's got a distribution. We call it a sampling distribution because it comes from samples. Centered, it's normal, centered on beta 1 with a certain amount of spread. Standard deviation is the square root of this, sigma over square root of SSXX. Again, not that we know what these numbers are. We don't know what beta 1 is typically, and we don't know what sigma is typically. I'm just, with the simulation, just pretending I know them. And if we know the distribution of capital B1, probably that means we can do inference on beta 1. We can estimate it with capital B1, or maybe a confidence interval centered at the observed value of capital B1 with a certain margin of error. And maybe we can do hypothesis testing on beta 1. Maybe the null hypothesis is that beta 1 equals like in the simulation, equals 0.5. And the alternative is that it's not equal to 0.5. More commonly, the typical null hypothesis you make when you're doing this kind of thing is to assume beta 1 is 0 versus the alternative that it's not 0. And if you reject the null, it kind of makes you happier, because then you're like, okay, I've got a significant linear regression. I'm pretty confident my slope is not 0. That makes it more interesting. It makes it more worthwhile to do regression. So what are the formulas for the confidence interval and the test statistic? That's in section 11.3. I sort of hinted last week that we'd get through 11.2. Well, actually, we're going to go through 11.3. Though, again, it's not that you need to know every single detail. You need to focus on the highlights. Confidence interval to estimate beta 1 is this one right here. B1, your point estimator, plus or minus your margin of error, which is a t value times the standard error. S over square root of SS. Okay, the book writes it as SXX, but I say SSXX. I'll write that down here. 100 times 1 minus alpha percent confidence interval to estimate beta 1 has a natural unbiased point estimator B1 plus or minus a margin of error. The margin of error is T sub alpha over 2 times S over square root of SSXX. This looks similar to that, doesn't it? But not exactly the same. SSXX, since the x's are fixed given numbers, is just a constant. And it's the same constant in both cases. It's not a random variable. Sigma is a constant. What's this S? It's a random variable. Is it a sample standard deviation? Not exactly, actually. S is the regression standard error. It does kind of act like a standard deviation, but it's not technically in the usual sense. Its formula is SSE divided by n minus 2. Not n minus 1. And this T value, this critical T value, is based on n minus 2 degrees of freedom, not n minus 1. Why is it based on n minus 2 degrees of freedom? Because it turns out when you square the regression standard error, when you divide by n minus 2, you get an unbiased estimator for the sigma squared. S squared, the squared regression standard error, is an unbiased estimator for sigma squared, the variance of the EIs. And by the way, the variance of the EIs is also the same as the variance of the YIs. YI is this constant plus EI. Its variability is the same. YI has the same variance, sigma squared. A different mean. This is its mean. It's not centered at 0, but it's got the same variance. Wild enough for you? And the reading's even wilder, right? If you tried doing the reading, you probably gave up, right? It's just like, looking at all this stuff. It is actually understandable if you took the time to do it, but it takes a while. It uses nothing but properties we've already talked about to this point. It's just that with all the summations and so forth, it just is really difficult to wrap your mind around unless you really concentrate and try some of the calculations yourself. It's based on some convenient formulas that are in this box, properties of summations, that are not obvious. Proving these it's not super difficult, but it's not obvious why these should work. So there's your confidence interval. What about a hypothesis testing? What kind of test statistic would you use? You'd use this one, page 395. That's the test statistic when your null hypothesis is beta 1 is 0, which is the most common null hypothesis to do. It's a t statistic with n minus 2 degrees of freedom. It's B1 effectively minus 0 in the numerator, because that's the null value, divided by standard error. S over square root of, okay, I would write that as SSXX. It really is the same kind of thing we always do, right? Think about computing a z statistic. It would be typically x bar minus mu 0 divided by, well, sigma over square root of n, and a basic t statistic would be x bar minus mu 0 over s over square root of n. I guess I'm using lowercase letters here, so these are observed values. Take the observed value of the statistic in question minus the null value from the null hypothesis divided by something that's typically called a standard error. It's an estimator for a standard deviation of this, in this case, which was the standard deviation of X bar, the variance of X bar, sigma squared over n, take its square root. Standard deviation of X bar is that. S over square root of n is an estimator for it. This test statistic for beta to test this null hypothesis has the same kind of form. Estimator minus 0 in this case, divided by standard error. S over square root of SSXX is the exact same thing that you see there. Can we do confidence interval and hypothesis test for the intercept instead of the slope? Page 398, test statistic to see if the intercept 0 or not. Oh, even more complicated. Confidence interval for the intercept. Page 398. Formulas are even more complicated. The general idea is the same. There's a couple more things we can do. Start at the bottom of page 398. Inferences about the estimated mean at the bottom of page 398. And also inferences about a single predicted value. What in the world is going on there? So far, the last 15, 20 minutes, we've been talking about inference related to beta 0 and beta 1, the intercept and the slope of the population regression line. Starting at the bottom of page 398 and going through page 404, it's about something different, but still plenty important. We will go back to the spreadsheet here. Hang on. We can come up with confidence intervals, 100 times 1 minus alpha % confidence interval, to estimate the mean of y when you know x. Inferences about estimated mean. Estimate for the curve of regression, essentially. Population curve regression, we want to estimate with a sample curve regression, you might say. Although, yeah, okay. That comes from the actual sample line, sample regression line itself. Notationally, initially we write this the point estimator as mu sub y given x hat. Hat indicating it's an estimator, plus or minus a margin of error. What is the margin of error? It's T sub alpha over 2 times the standard error. What's the standard error? I'm going to see if I can do it from memory. It's the regression standard error, capital S, times the square root of 1 over the sample size plus x minus x bar squared over SSXX. I'm going from memory there. I didn't peek at the book. Taught this a fair amount. Let's look at and see if I got it right. It's at the bottom of page 399. Yeah, it looks good. Again, I call it SSXX, whereas the book just labels it SXX. I want to remind myself it's a sum of squares. Keep it clear in your mind what everything represents. N is the sample size. X bar is the mean of the x's. SSXX is sum of squares of the x's. We've written down that before. What's x itself? It's a lowercase x there. It's whatever you want it to be. You can use this for any value of x. Though I will say, this is typically more valid in a practical sense if you use it for what's called interpolation instead of extrapolation. Pick a value of x that's not higher than the maximum value of x that you actually gather data for and not lower than the smallest value of x that you gather data for. That's called interpolation. Extrapolation is when you go too far to the right or to the left. The model may no longer be valid if you go too far to the right or to the left. What's mu hat? Mu hat is none other than B0 plus B1x. Using capital letters there because it's a random variable. But of course, once you've got data, then they become observed values and you can use lowercase letters. You got to use the regression line to find your point estimate. And then find all these other things to find the margin of error. And the degrees of freedom, so once again, n minus 2. With regression, with simple linear regression, df is always n minus 2. In applied stats, whether I teach it or Dr. Wetzel teaches it, chapter 12 is something we get to. It's called multiple regression. You got more than one explanatory variable, more than one x, so to speak. Maybe you call the variables x1, x2, x3 through xn or something. Well, and it would be a bad thing to use, maybe through xk, I think is what the book uses. If you've got two explanatory variables instead of one, df becomes n minus 3. If you got three explanatory variables, it becomes n minus 4. 4 explanatory variables, it becomes n minus 5. K explanatory variables, it becomes n minus k plus 1. N minus k minus 1, if you've got k explanatory variables. We're not doing that. But that's what happens. That's how you figure out the critical value here, t. So this gives you a confidence interval to estimate essentially your population regression line for different values of x. For any given value of x, you're going to get one interval. For another value of x, you'll get a different interval. There's also one more thing. This is the last thing. I think this is the last new thing of the semester right here. 100 times 1 minus alpha percent PIs to estimate something. PI, huh? It's no longer a confidence interval. It's called a prediction interval. But guess what? Even though we call it a prediction interval, it's still a confidence interval. We use the word prediction to highlight how it's used. We're using this interval to estimate a population parameter effectively. We're using this interval to estimate y itself. To estimate a single predicted value. And the notation is a little different. The point estimator is y given x hat plus or minus t sub alpha over 2 times the standard error. And the standard error looks almost exactly the same as that, with one seemingly slight difference. Under the square root, you also add 1. Now, you might think that adding 1 there doesn't make a big difference, but it actually can make a humongous difference as far as how big the margin of error ends up being in a given situation. It can make a humongous difference. Why? In maybe an idealized situation, n is a very large number. You got a large sample size. So 1 over n, if n were 100, 1 over n would be 0.01. And you see it in both formulas. These fractions also could be very small. For example, they could be 0 if x equaled x bar, they'd be 0. If x is slightly different from x bar, they'd be small numbers. Even if x is kind of far away from x bar, it's possible these fractions could be small because SSXX could be a very large number. So in both cases, these two fractions tend to be pretty small numbers. If the sum of these two things is very small, like, I don't know, 0.02, and you take its square root, it's still a small number. By adding 1 there, you're changing it from a very small number to, well, not a very small number, 1.02. Take its square root, it doesn't change much. For this numerical example on my calculator, I get a margin of error that is about 7 times bigger for the prediction interval than for the confidence interval, because this number is about 7 times bigger than that number. 7. So that means the interval in this numerical example, this interval is 7 times wider than this one. There can be a big difference between these things. But wait a minute, we still got to beg a question here. How do you compute that? Guess what? It's the exact same thing as that. You still use the regression line. It's just a different symbol for it to emphasize its different purpose. Here we're trying to estimate, again, a population parameter, the mean of y when you know x. Here we're trying to estimate the value of y itself when you know x. It should make sense that we're less certain of the value of y itself than we are of the mean. This margin of error is smaller than this one. Should make intuitive sense. But a weird thing that happens in both cases is that if x goes further away from x bar, these intervals get bigger, because in both cases, you've got these fractions that have a numerator equal to x minus x bar squared. So if the value of x you're thinking about using these for is far away from x bar, it's going to make you have big margins of error. On the other hand, these are as small as possible when x equals x bar. And this is illustrated in the book. With some graphs. There's the one on page 400. 402's got another one. This is a better one. Page 402. So this line right here, this blue line, is your sample regression line, not necessarily the population regression line, right? Population regression line will be a little different. For each of these values of x, you've got 4 other curves colored black. The 2 that are closest to the blue line form the confidence intervals to estimate mu. It's labeled 90% confidence band on mu y given x. Could have been interval instead of band. It's a vertical interval here. For that value of x that's close to 1.6, it's telling you that mu is likely between second coordinate of the lower point and second coordinate of the upper point, between about 15 and close to 15.5. But for a different value of x, you get a different confidence band. Like if x is 1.4, you get a band that looks like this. These bands you can see are getting wider the further away you get from the middle. X bar is somewhere in the ballpark of, well, wherever this confidence band is skinniest, maybe right about there, close to 1.5. That's the value of X bar. And as you move away from X bar in either direction, they get wider, they get further apart. Same with the prediction band or prediction interval in each case. Distance between the outer 2 curves. Smallest close to 1.5. Gets larger as you move away. Kind of reflecting the fact that you're more sure about interpolating than you are about extrapolating. Is the effect of this. Okay, for our remaining time, what's probably most useful for the sake of homework to go back to the spreadsheet and probably go back to the example from last Thursday, the quiz scores. And let me redo the calculations I was showing you at the end of class last Thursday. And also do something new that will be handy for you, both on homework and possibly on the final exam to know about this. So first I'll remind you what we did. So I got quiz 1 scores, quiz 2 scores, n is 10. There are 10 data points. We use equals SUM to add up the numbers. Copy and paste it over. For the means, just divide by 10 or do equals average. Standard deviations, do equals STDEV. Correlation. Is correlation discussed in the book? Yeah, though not until later in the chapter. It is a measure of strength of the linear trend. 2 R's, 1 L. Again, it says data Y comma data X, like you should do Y first, then X. It really doesn't matter. I think the reason they do it that way is to emphasize you're trying to predict Y when you know X. But as far as the calculation itself goes, you get the same answer either way. 0.778. Positive. That's reflecting that the slope of the regression line is positive. And closer to 1 than it is to 0. So you might think intuitively, maybe that means that's a fairly strong linear trend. Well, actually, the squared correlation is a better measure of the strength of the linear trend. R squared. So a little closer to 0, though not a ton closer to 0. It's close enough to 0.5 to call this a moderately strong linear trend. By the way, the squared correlation has a name besides squared correlation. It's called the coefficient of determination, but you don't need to know that for the exam. With the spreadsheet, I'll remind you also there's another formula for the slope. Using the correlation, R times standard deviation of the Y's divided by the standard deviation of the X's. You remember that? I did mention that last week. Is that in the book? I think it is. I'm forgetting what page. Let's look through the book quick. to see if we can find that formula. It's just another formula for the slope. I think it's here. I'm just forgetting where. Oh, I suppose it couldn't be in here until you talk about correlation. It's actually the very last section. Okay, I'm not seeing it. Wondering about maybe the last couple pages here. I think I'm not going to take the time to do it, but I think the stuff at the bottom of page 424 can probably be used to derive it. But I'm not going to take the time to look that out over and check and see if it works. It's page 424. But it is true that, let's write it in terms of observed values. Little b1 is the correlation little r divided by the standard deviation of the y's, or times the standard deviation of the y's divided by the standard deviation of the x's. That is a formula that will give you the slope. But you got to know the correlation for that to use it. Intercept is y bar minus the slope we just found times x bar. Okay, first thing to do is confirm these answers with the other formulas in the book. So we need a column for the x squared values and a column for the x times y values. I'm thinking about using the formulas in the book here to double check these numbers, because I'm going to have to add those things up by summation of the xi squareds and some of the summation of the xi's times yi's. I did this last Thursday. So here are the squared x values. Here are the x times y values, xi times yi values. We can add those up, those columns. We can use these numbers to find, well, one way to do this is to find SSXX and SSXY. And to do that, I'm going to use not these formulas, but these two formulas, the numerator and denominator of this fraction here. I don't think I did this last Thursday. SSXX is the sum of the x squared values minus the sum of the x's squared over 10. Maybe I did do this last Thursday. 14.9. SSXY is this summation minus this times this over 10. And the ratio of those two should be the slope. If I do SSXY divided by SSXX, I get the same answer, 1.02. To believe the formulas, right? There's following the formulas theoretically, and then there's believing them by actually trying examples. Let's do more. Let's also find predicted values of y hats, I'll call these, using the regression line, the slope and the intercept from cells B17 and B18. If I'm going to copy and paste, I'll need dollar signs equals $B $17 is the slope times x plus B18, $B $18. gives you a predicted y from the regression line. I'm using the regression line right now. Person who scores 8 on quiz 1 is predicted to score 8.3 on quiz 2. Now, that can't be right if we only allow whole number quiz scores, or even if we only allow half point quiz scores 8.5 or something. But it's just what the model predicts. These are the different y hat values for the different x values. The bigger x is, the bigger y hat will be because the slope is positive. And x is 10, this is the biggest y hat value, higher than the points possible in quiz 2, assuming they're 10-point quizzes. It's okay. Y minus y hat is a residual. Oh boy, I gotta go quick here. I think I'm gonna have to share with you something else over a video instead of, because we're running out of time. Do each y value minus each y hat value. So this 0.697986 is 9 minus 8.3. The next one is going to be 9 minus 9.3, negative 0.3. 9 minus 9.3. These are the residuals. Sometimes negative, sometimes positive. These are effectively modeling sigma, standard deviation of the EIs. By the way, if you add them up, you get effectively 0. They have to average out to 0. But if you square them, they don't have to average out to 0. Squared residuals and why am I doing this? Why am I squaring these things? Because when I square them and add them up, I get our old friend SSE. That's why. Sum of the squared errors. Residuals, 10.09. This is the smallest possible value of SSE over all possible regression lines. The least squares linear regression line minimizes SSE. That's what we did with the partial derivatives last week. If I divide it by n minus 2, I get an estimate for S, regression standard error. S. Divided by, you know what? I think I wrote the wrong formula. Yeah, I forgot to take a square root. Should have had a square root here. This was like 40 minutes ago. Maybe not quite so long ago. When we were doing our confidence interval to estimate beta 1, S, the regression standard error involves a square root. Bad mistake. Hang on. So I got to do the square root of that. Your square root of this divided by n minus 2. N minus 2 is 8, since n is 10. 1.123 is our regression standard error, the observed value of S, that comes up in these other formulas. That's the number you would use right there, right there, right there. And was there one more place? I think there was. Where's my, I guess we looked in the book at the statistic for doing the hypothesis test about whether beta 1 was 0 or not. Okay. The thing I want to share with you in a little bit is another video where I've shown how to download something called Excel minor analysis tool pack for your spreadsheet that will do a lot of regression stuff for you like that. But you got to know how to read the output. So the hard part is reading the output. I've done a video where I talk about that. I'll share that with you. Okay. Have a good day.